So good evening, one and all. Third unit we will discuss today methods of estimation, maximum likelihood, moments, and minimum variance. So methods of maximum likelihood, method of minimum variance, method of moments, method of least squares, method of chi-square, and method of inverse probability. So method of maximum likelihood estimate we have taken here. The most widely used method of estimation of method of maximum likelihood estimation is initially formulated by C.F. Gauss, but its general method was introduced by R.A. Fisher. We know that. And also, let x1, x2, x3, xn be a random sample here, drawn from population with a PDF probability density function f of x comma theta, then joint density function x1, x2, x3, and so on xn is given by f of x1, x2, x3, and so on xn. Therefore, f of x2 theta into f of xn theta is equal to xn theta pi I is equal to 1 to f of x theta. The above function is known as maximum likelihood function. It is denoted by Li is equal to 1 to n f of x theta x theta. అంటే pi is equal to 1 to n f of x theta and Li x theta రాస్తే the likelihood function, because a sampling distribution when taken a function of x1, x2, x3, xn for a different center of sample values here, so therefore the information will be different. So maximum likelihood function can be written as Lx minus theta, xi comma theta. And also computation process finding of ML estimator. To find ML estimator for the parameter theta, maximize likelihood function with respect to theta, that is rho L by dou theta is equal to 0 and dou square L by dou theta square. We are taking the partial derivation of first equation and second equation, that is less than 0. Theta is the estimate and obtained from the equation dou L by dou theta is equal to 0 and L is the probability value and the value is always positive. Since L is the product of n functions, its difference will be easier with logs. So L is maximum when log maximum log is maximum replacing L by log L. So therefore dou L by dou L by dou theta is equal to 0. As a probability value, its value as always positive, since the n functions differentiation will be easier with log. L maximum, what is the log? When log is maximum replacing L by log L, so estimated theta is solution of the equation dou log L by dou theta is equal to 0. There is a partial differential dou square L by dou theta square less than 0 here. So dou square L by dou theta square, the first and the second order derivative, the first and second order derivatives are dou log L by dou theta and dou square log L by dou theta square. The first differentiation and the second differentiation of the partial differentiation less than 0, the condition is exists. The continuous function of theta is range R. For every theta in R, modulus of dou log L by dou theta less than f1x and dou log L by dou theta less than f2x. So f1x and f2x are integrable functions of minus infinity to infinity. So therefore, the third order derivative dou cube log L by dou t square, such that the dou cube log L by dou t square less than mu x, where e mu x is k, is positive equantity. And see here, for every theta in Re minus dou square L by dou theta, that is integration of R, minus dou square log L by dou theta square, that is dx1, dx2, and so on. Dx and I theta is finite and non-zero. The range of integration of independent of theta and differentiation under integral sign is valid. Properties of MIL estimators. What are the properties? ML estimators are constant. ML estimators are most efficient. ML estimators are sufficient, constant, and efficient is sufficient. Distribution of ML estimator tends to normality for large sample with the variance given by 1 by V theta minus NE dou square log L f of x I theta minus dou theta square. So ML estimators have invariance property. That is theta cap is ML estimator. Theta then f of theta cap will be ML estimator for theta. ML estimators are not necessarily unbiased. Steps to compute ML estimators under asymptotic variances here. Let us f of x comma theta be a family density x1, x2, x3 and so on. Xn be a random sample size of, then we know L theta phi of I is equal to 1 f of xi theta. Write down the likelihood function, maximum likelihood function L theta. Consider long likelihood function L theta. Find dou log L by dou theta. Solve dou log L by dou theta of ML estimator. So therefore, E is equal to minus dou square L by dou theta square. This is asymptotic variance of ML estimator of 1 by theta. So we can see one example here. Obtain ML estimator for the parameter alpha in a gamma distribution with PDF f of x comma alpha e power minus x power alpha minus 1 gamma alpha x greater than 0 and alpha greater than 0. What is the fundamental problem we are taking here? So therefore, the solution let xi is equal to y, I is equal to 1, 2, b, 3, 4 and up to the n, the random sample size of n. So consider the likelihood L alpha is equal to phi is equal to 1 to n xi minus alpha. Phi is equal to 1 e xi minus xi alpha minus 1 gamma alpha. The condition is e power minus summation of xi pi I is equal to 1 to n xi alpha minus 1 gamma alpha whole power n. Now consider the long likelihood function log L alpha minus summation of xi alpha minus 1 log phi is equal to 1 to n. And the condition we are expanding here xi minus n log gamma alpha. So therefore dou log alpha minus dou x is equal to 0. So therefore summation of log xi is equal to n by gamma alpha or gamma alpha whole square, gamma alpha is equal to 0, the condition of satisfying here. Therefore log we are taking here log this condition E of log xy log of 9 minus 1 nxi minus n gamma alpha 1 is equal to 0. We are taking the condition here also, this one. By solving the above equation, the ML estimator can be alpha can be obtained here. Consider the binomial distribution with the density function we are taking here f of x comma p ncx. This is ncx we are writing here. Px p power x and p1 minus pn minus x is equal to 0 1. So that ML estimator p is x by n and find its variance also we are taking here. Therefore, f of x comma p ncx v power x 1 minus p power n minus x. So in this condition x is equal to 0 1 2 3 4 and so on n. LP is equal to ncx p power x 1 minus p whole power n minus x. F of x comma is the probability out of n trials itself likelihood function. Consider the LP log L log ncx plus x log p n minus x log 1 minus p. So dou log p by dou p, so the partial derivation of first one. So the partial derivation of first one we are taking here xp by n minus x 1 minus p is equal to 0. So in the LCM we are taking here, it is a p and 1 minus go, that is x minus np. The partial derivation we have, what is the value output here is equal to x by n. The ML estimator p is x by n. We are taking here the PL x by the PL, the ML p is equal to x by n. So therefore the ML estimator p is equal to x by n we are taking here. Dou square log LP by dou p square minus x by p square minus n minus np by 1 minus p whole square. 1p, the condition we are taking here 1p dou square LP by dou p square is equal to NP by P square plus N minus NP by 1 minus P square. Therefore, P is equal to 1 by X by N. The condition is N by 1 minus P. So, therefore, it is P into 1 minus P. But the asymptotic variance of MLE, P is given by value is given here. Find the ML estimator. Theta is based on the random sample and n observation drawn from a population with the following probability density function f of x comma theta 1 plus theta all for x for theta greater than 0 and theta less than or equal to x less than or equal to 1 we are taking here. So give the probability density function f of x comma theta 1 plus theta x for theta theta greater than 0 theta less than or equal to x less than or equal to 1. Consider the likelihood function phi is equal to I is equal to 1 to n f of x comma theta. So we are taking the bracket here also. Phi of I is equal to 1 plus theta xi theta 1 plus theta phi is equal to 1 to n xi theta. Considering the log likelihood function we are taking here. So log theta, so applying the log from the both side, n log 1 plus theta plus summation of I is equal to 1 xi. So dou log L theta by dou theta is equal to n by 1 plus theta summation of I is equal to summation of dou log L by dou theta is equal to the condition is partially differentiation is equal to 0. So therefore we are taking here n by 1 plus theta summation of I is equal to n log xi theta is equal to 0. So 1 by n plus theta minus summation of I is equal to 1 log xi. So 1 plus theta is equal minus n summation of I is equal to 1 log xi we are taking here. So theta is equal to 1 plus the condition has been as per the above condition. So we are taking the one side here theta here. So it should be minus here, minus of 1 minus 1 plus n log minus common. It should be minus common minus into minus 1 plus n. We are taking the common here automatically. It will be changing the values of the left and right side. The theta is one side is there. But is the given theta greater than 0? Thus, the method of differentiation fails to get estimate of theta. Then aims to choose the theta such that L theta is maximum of L theta. Is maximum of theta is maximum, but is also given that theta less than or to x. The maximum value which takes theta is the minimum of the sample values. The sample values are arranged in ascending order. In the minimum samples, x1 will be the required estimate of a theta. Methods of movements. Let us discuss another method obtaining estimate discovered by Carl Pearson of methods of movements. Methods of movements discovered by Carl Pearson. Let f x theta 1, theta 2, theta 3, theta 4, and theta k be the density function of a point parent population with k parameter theta 1, theta 2, theta 3, theta k. We know that the rth moment about the origin u r dash is equal to integration of x 4 r f of x1 x theta 1, theta 2, theta 3, theta k dx r is equal to 1 to k. In general, mu1 dash, mu2 dash, and so on, mu k dash are the functions of the parameter theta 1, theta 2, and so on, theta k. That xi is equal to I is equal to 1, 2, 3, and so on n with random sample of size n drawn from population with density function f of x theta 1, theta 2, theta 3, and theta k. The methods of movement consist of solving k equations for theta 1, theta 2, theta 3, theta k in terms of mu1 dash, mu2 dash, and so on, mu k, mu dash k. So theta I cap, theta I that is mu1 dash, mu2 dash, mu3 dash, and mu dash k it I also same m1 dash m2 dash and m3 dash mk dash అంటే అక్కడ m1 dash తీసుకుంటే లాస్ట్ వరకు వచ్చారు m1 dash తీసుకుంటాం. So when mi is the ith moment about the origin of the sample we are taking here. So properties of the sample movement. So what are the properties of the sample movement? Sample movement is consider consistent estimate of the population movement. These estimators less than efficient of MLEs in case of the polynomial populations of the both estimators are coincide. The method would fail to give estimators where the population movements do not exist. The estimators are asymptotically normal variates. An example we have to take here. Using the method of movements, find the estimate of the parameter lambda and sampling of from population. What is the sampling of population? So p x comma lambda e power minus lambda lambda for x factorial x is equal to 0 1 we are taking here. So solution, consider the sample here xi is equal to 1 2 3 and so on n. So sample movement. So sample movement here about the origin mi dash is equal to summation of xi by n x bar. So we know first moment of the distribution about the origin. So in the first moment of the about the mu origin is equal to we are typing mi dash is equal to summation of xi by n x bar. That is u1 dash f is equal to summation of x equal to 0 infinity e power minus lambda lambda x by x factorial. So therefore, e power minus lambda summation of x is equal to 0 to infinity x into lambda power x x factorial. So therefore, lambda into e power minus lambda summation of x is equal to 0 to infinity lambda x power minus 1 by x minus 1 factorial. So lambda into e power minus lambda, that is we are simplifying here 1 plus lambda lambda square plus 2 factorial lambda cube by 3 factorial and so on. So lambda into e power minus lambda into e power lambda, that is a simplification of this one. This one we have read here e power lambda. This is from 3.1 and 3.2 we get mu1 dash is equal to lambda is equal to x bar. Lambda x bar is the estimator for the lambda we are taking here. Another example, estimate A and B from the following Pearson type 3 curve by the method of movements. F of x comma b, b a comma b power a plus 1 gamma a plus 1 x power a e power minus b 0 less than x less than infinity. So we are taking another solution. We know that mu r dash f of x comma b dx integration of 0 to infinity x power r b power a plus 1 by gamma a power plus 1 x power a e power minus a b x dx. So therefore b power a plus 1 by gamma a plus 1. So integration of 0 to infinity x into a plus r e power minus bx dx. So let us bx plus t. So let us bx is equal to t, x is equal to t by b. So we are differentiating with 1, dx is equal to dt by b. So mu dash r is equal to b power a plus 1 by gamma a plus 1 0 to infinity of integration 1 by t by b a plus r. So therefore e power minus t dt by b. So therefore simplification of this one b power a plus 1 gamma a plus 1 automatically here. This is the same here of b I r plus 1 into infinity. This is a simplification one we are taking here t a plus r plus 1 and adding minus 1 plus 1 and adding minus 1 to above it will become e power minus dt. 1 by gamma plus 1 we are cancelling bar plus 1. So this is the we are taking here. So b power r we are taking here. So therefore gamma of a plus r plus 1. So we are taking the solution mu1 dash is equal put r is equal to 1 we are taking here 1 by gamma a plus 1 b. Gamma a plus 2 is equal to a plus 1 by b we are writing here. So put R2 is equal to mu2 dash equal to 1 by gamma a plus 1 b square gamma a plus 3, that is a plus 2 into a plus 1 by b square. So mu2 is equal to mu2 dash by mu1 dash whole square, that is a plus 2 a plus 1 by b square by b square into a plus 1 by b whole square. So therefore mu2 is equal to, after the simplification, b square cancel here, a plus 2 by a plus 1, there is a b square cancel, and a plus 1 whole square is equal to also the simplification of the multiplication. We done a plus 1 by a plus 1, that is, so is equal to 1 by a plus 1. There we are taking the LCM here. So therefore mu2 dash by mu1 dash whole square is equal to 1 by a plus 1 plus 1. So a plus 1 is equal to mu1 dash whole square minus mu2 dash minus mu1 dash whole square. A is equal to mu1 dash whole square minus mu2 dash minus mu1 dash whole square minus 1. So therefore A is equal to 2 into mu1 dash whole square minus mu2 dash minus mu dash 2, mu2 dash whole square we are writing here. So therefore mu1 dash a plus 1 by b is equal to b, a plus 1 by mu1 dash is equal to 2 mu1 dash whole square minus mu2 dash minus mu1 dash whole square by mu1. That is the conditions we are taking here. So therefore b is equal to mu1 dash minus mu1 dash minus mu1 whole square. This is the condition 1. Method of minimum variance. So method of minimum variance is the procedure of determining an unbiased estimator with the minimum possible of variance. T is the maximum variance estimator of theta for distribution of f of x comma theta. Then T is then T is determined by such E of f of is equal to theta. That is also V of T is minimum possible. Why the variance of the T is minimum possible we are taking here. Let us consider above the condition that E power theta is equal to V power T minimum possible we are taking here. Integration of LT dx is equal to theta. Integration of T E power T whole square LDX. Integration of T minus T whole square LDX. So minimum possible differentiate above with respect to theta. T into dl by theta of dx is equal to 1. To get minimum variance of the estimator of the integration of t minus theta whole square we are taking here, subject to integration of t into dou L by dou theta, we are partially differentiating the dou L by dou theta. Theta is equal to 1 we are taking here. This is a theta, but it is a 1 here. Let us define phi is equal to t minus theta whole square L minus 2 minus lambda into dl by dt we are taking here. Where lambda is a function of theta and independent sample observations. Fulfillment of 3.3 is equal to the fulfillment of dou phi by 2 d is equal to 0. Dou phi by 2 d is equal to 0. That is a condition of 2 into theta minus 2 minus lambda dou L by dou theta is equal to 0. That is a condition we are taking t minus lambda by L. So integration of 1 dou L by L d theta is equal to dou log L by dou theta we are writing here. Let us prove that v theta is equal to consider integration of minus infinity to infinity t minus whole square del dx. What is the t minus whole square? We are clearly writing here in the above condition. We are writing here. So integration of lambda square dou log L by dou theta whole square of L dx. So minus lambda 2. We are taking the common of minus lambda. So take dou square log L by dou theta square is equal dou log L by dou theta square is equal. That is a minus coming here, minus dou square log L by dou theta square also. We are simplification of this one. We can write here this one also. V theta is equal to minus, this is lambda square. So minus lambda square integration of dou by theta is equal to dou log L by dou theta L dx. This is now lambda square, it will become. Minus lambda square integration of dou by dou theta. So dou L by dou L t minus theta by theta L dx minus lambda square t minus theta by dou theta 1 by theta into dou by theta 1 minus theta L dx we are taking here. Minus lambda square theta minus theta dou by dou x of 1 by lambda L dx plus lambda into lambda of L dx. So therefore minus lambda square dou by dou theta of 1 by 1 is all integration will be simplified here. Lambda integration of L dx we are taking here. So since mu1 is the first moment about the mean and 0 and integration of L dx 1 and the above expression reduced v of t is equal to lambda. The condition of this one we can write here t minus theta by vt dou log L by dou theta. The condition is verified here. So another theorem we have to learn here. A random sample of x1, x2, xn, and so on. Xn is taken from population with mean 0 and variance sigma square. Examine summation of xi square by n is the minimum variance unbiased estimator of sigma square. Find the minimum variance. So consider the probability density function of the normal distribution 1 by sigma under root of pi e minus x square by e 2 sigma square. Replace sigma square by theta, then f of x becomes 1 by sigma root pi e power minus x square by e power 2 theta. L theta pi is equal to 1 to n f of x I theta 2 pi I. So 2 pi I we are taking here minus 2 pi I we are taking here minus n by 2 power e minus summation of I square. So at a condition ni manam akkada pi I is equal to 1 x I theta 2 pi I lo తీసుకుంటే minus n by 2 power e summation of I square by 2 theta గా మనం రాసుకుంటాం. So therefore L theta condition తీసుకుంటే minus n by 2 log of minus n by 2 log pi log theta plus log 2 pi. So minus of e condition as is rastam minus of summation of s square theta. So partial derivation dou log L by dou theta is equal minus 10 by 2 of 1 by theta. Again summation of x square by theta minus common తీసుకున్నాం ఇక్కడ. So minus n theta, take the LC minus n theta summation of y square by theta square. So summation of y square by n by 2 theta square n by minus theta. So dou log L by dou theta is equal to summation of xi square by n minus theta 2 theta square by n. So summation of x square by n minus sigma square 2 sigma square by 2 sigma power 4 by n. So summation of x square by n is the maximum variance unbiased estimated sigma square is the minimum variance 2 sigma power 4 by n. So this is one of the example here. Find the maximum variance unbiased estimator for lambda when samples is drawn from a Poisson distribution with the density function e power minus lambda power x factorial. Consider the PDF Poisson distribution e power minus lambda power x factorial, that is x equal 0, 1, 2, 3, 4. The likelihood function L is given by Lx phi is equal to 1 to n f of x1 minus theta e power minus n lambda summation of xi, that is pi into x factorial. So therefore log L minus n lambda plus summation of xi log lambda. So minus log xi we are writing here. The partial derivation we are taking here dou log L by dou lambda minus n plus summation of xi lambda. Dou log L by dou lambda minus summation of xi minus n lambda by lambda. So therefore the condition dou log L by del minus summation of xi minus n minus lambda by n. So we have n cancel here, that is the condition t minus lambda by vt. So therefore summation of xi by n x bar is the minimum variance unbiased estimator lambda as the variance is lambda power n. This exercise is the more important questions for this unit here. Next we will go to another unit. Next, testing of the statistical hypothesis, concept of testing of hypothesis, problems based on Neyman-Pearson lemma, test for single mean and proportion we are taking here in this estimation. So concept of testing of hypothesis we are taken here. Simple hypothesis, composite hypothesis, null hypothesis, alternate hypothesis, statistical hypothesis. In this statistical hypothesis, critical region, type 1 error, level of significance, type 2 error, power of the test. All these one learned in this. Some of the topics we are learned in the 5th semester design of experiment here. We can take the introduction here. In the previous, we have studied the problem of estimation, both point and interval estimation. It forms the first part of statistical inference, testing the statistical hypothesis, the second part of the statistical inference. So statistical hypothesis, second part of the statistical inference we are taking in our daily life. We come across several situations involving test of validity of rival claims. For suppose a person wants to purchase two-wheelers, several brands of two-wheelers and two-wheelers available in the market and several criteria like fuel efficiency, cost, safety, and after sales services, etc. can be used in the selection. Other things be more or less, more or less equal. Suppose a person wants to useful efficiency as an important criterion and narrows down to his search the two brands A and B. The manufacturers of each those brands are claiming that the brand is superior to other. Now the main problem being faced, which of the claims is correct. Suppose we put N1 to two-wheelers, brand A1 A brand A and N2 brand B on test based on that condition here. Information we want to come addition of validity with the rival claims are made such content using what is the statistical statistical test of hypothesis. Definition of statistical hypothesis. Definition of statistical hypothesis. Suppose x denotes the random consideration. Let f of x comma theta we are taking here. So denotes the probability mass or density probability mass or density function. Theta belongs to h. The unknown parameter involved in the probability function. What is the unknown? So we let f of comma t theta denotes it's the probability mass and the density function. Theta belongs to h is the unknown parameter involved in the probability function. Any assertion or statement about the unknown parameter theta involved with the probability mass density function is called as statistical hypothesis. That h1 subset are equal to h, h2 that is h minus h1. So theta belongs to h1 or theta belongs to h2 for statistical hypothesis. What is simple hypothesis? A statistical hypothesis simple hypothesis, statistical hypothesis is called as simple hypothesis. It is specifies the probability distribution of completely. The following are examples of the simple hypothesis. So x equals to be 10 minus, so 1 t minus theta is equal to 0, 1 by 2. X p theta is equal to 1, x equals to n. That is a, you can call a simple hypothesis equal to b equal to p equal to n. There is mu is equal to 0 and sigma square is equal to 1. We are writing here. In case of all, there will be a single probability distribution under consideration. Composite hypothesis. The statistical hypothesis is called as a composite hypothesis. It did not specify the probability distribution completely. X equivalent to be 10 minus theta 0 greater than 1 by 2. So x equivalent to greater than 2, lambda greater than 2. X equivalent to n mu minus sigma square mu is equal to 0. That is also band mu greater than 2. Akkada 1 equal to 2 or sigma square greater than 2 is as compositive hypothesis. All are compositive hypothesis delta greater than 2. Null hypothesis. Hypothesis of no change or no difference is called null hypothesis denoted by HO. So in the example given, the introduction, let mu A and mu B denote the fuel efficiency of the two brands A and B of the population. If we start with the assumption mu A greater than mu B, then B will accuse. We have started with the prejudiced notation. If we take mu A greater than mu B, then it will be the turn. By turn, because mu A greater than mu A less than mu B, or assumption of mu A greater than mu B, or mu A less than mu B, then it will be the turn on A to accuse us. So the best course of action to start with assumption mu A is equal to mu B. This assumption mu A is equal to mu B, there is no difference between two brands, equal efficient token. There is no assumption there. It is called as null hypothesis. No assumption is there. We can call that null hypothesis, alternative hypothesis. So alternative hypothesis we are writing here. Any hypothesis which alternative the null hypothesis is called as alternative hypothesis. It is denoted by H1. In the above example, we can have alternative hypothesis mu A greater than mu B, or mu B greater than mu A, or mu A not equal to mu B we are writing here. So mu A greater than mu B or mu B greater than mu A, heteroscopy value is difference or called as single-sided alternatives. That is mu A not equal to mu B is called two-side alternative. Mu A not equal to mu B we can call as a two alternative hypothesis here. In general, text x equivalence of x comma theta, theta belongs to h, and we are interested in testing. So theta belongs to h naught subset of h. Against h1 belongs to h1 greater than h1, so h minus h1. So if h theta 0, theta 1, then both the null and the alternative hypothesis are simple hypothesis. Hereafter we'll be considering this situation. Test statistical hypothesis. Suppose x1, x2, x3, xn, and xn is a random sample of size n taken from x, that is xi is equal to 1, 2, 3, 4, or n, are a set of independently or identically distributed, independently and identically, independently or identically distributed random variables having the same distribution. So therefore, on that x we are taking here. So a test of the statistical hypothesis decision, the rule criterion that enabled us to reject or not reject or accept the null hypothesis under the accept or reject in the null hypothesis under consideration we are taking here. So we can consider the sample x1, x2, x3, xn, and so on as a point n-dimensional space. We can consider subset of C of R power n and reject. The null hypothesis x belongs to C or do not reject x belongs to Z is a lit test of statistical hypothesis. It's a critical region. A subset of C, subset of R is called the critical region. Critical region means we are taking the decision of experiment also. C subset of R power n is called as critical region. The null hypothesis under the consideration is rejected whenever the sample point belongs to it. The critical region is also known the region consisting the set of values. The critical region set of the values మనం తీసుకుంటే అది null hypothesis ని reject చేస్తుంది. Two kinds of error in testing of statistical hypothesis. Suppose we are interested in testing h naught is equal to theta t naught against h1 theta is equal to t1 based on the information supplied by a sample taken from the population. Then the four situations can be described in the following table. So we are taking here decision taken, actual situation, h1 h naught is true, h naught is false. So actual situation and do not take decision taken. We are writing here. See all of you. Actual situation do not reject HO. True అయినప్పుడు correct decision, reject అయినప్పుడు type 1 error. False అయినప్పుడు type 2 error, ఇది correct decision. చూడండి exact. True అయినప్పుడు correct decision. False అయినప్పుడు type 1 error, type 2 error. So therefore we are taking this one reject HO లో మనం ఈ రకంగా తీసుకోవాలి. Type 1 error. The error of the mistake that is committed in rejecting null hypothesis that is actually correct or true or false, type 1 error. The probability of committing type 1 error is denoted by alpha. It is called the level of significance or size of the test. Alpha, probability type 1 error, probability reject HO, H naught is true, probability X belongs to C, HO is true. So type 2 error. Type 2 error, the error or the mistake that committed is not rejecting the null hypothesis when it's marked as fault. అంటే అది కరెక్ట్ గా అయినప్పుడు కానీ ఒమిట్ చేసినప్పుడు null hypothesis లో the false is correct as type 2 error we are taking here. The probability of committing type 2 error denoted by beta. Beta probability type 2 error is called do not reject HO or HO is false. Do not reject HO or HO false. X does not belong to C, H naught is false. X does belongs to C, H1 is true. So therefore power of the set we are writing here. So power of the set of the we are writing here. So if B denotes the probability of the committing of the type 2 error, then 1 minus beta is equal to probability of reject HO or HO. Reject HO is false. So therefore X belongs to C by H1 is called power of the test. It is indicated probability of taking the correct decision. Some conditions here. In testing statistical hypothesis based on the limited amount of information obtained from a sample, we will sometimes commit type 1 error and other times commit type 2. Though we do not want to commit any error. The null hypothesis should be formulated in such manner that committing type of the error becomes more serious here in null hypothesis. It should be formulated in such manner the committing type or error becomes more serious here. Let phi is equal to r for n 0, 1, 1, 0, 1, this one. A function defined r for n is closer to 0, 1 such that phi of x if x belongs to C, 0 if x belongs to C, subset of r equal to n, then phi of x is equal to non-randomized test function. So, itla gonna C subset r equal to r for n unte C is called or the non-randomized test function. This is called the critical region. The choice of the critical region specify a test alternatively. A test specifies a critical region. There is no one-to-one corresponding between the two. So the terms and the critical regions are often synonymously. Example. X equivalent to P lambda to test H1 lambda is equal to against H1 lambda is equal to single observation taken. The null hypothesis is X greater than 3 we are taking here. So therefore find the probabilities of the committing type 1 and type 2 errors we are taking here. Also find the power of testing of H1. So see here. We have x minus lambda అంటే దాన్ని ఏం చేస్తాం e power lambda into lambda power x by x factorial. So lambda greater than 0, x is equal to 0, 1, 2, 3. So therefore that we are writing x by x greater than 3 we are writing here. Alpha is equal to probability x belongs to C, HO is true. Probability x greater than 3 by lambda minus 1, summation of x is equal to 4. E power minus 1 by x power 1. 1 minus summation of x is equal to 0, 3 e power minus 1 by x factorial. There is a simplification we are doing 1 minus e power minus 1. That is 1 plus 1 by 2. And simplification of 1 no, second 1 no, the 1 by 2, 1 by 6, 1 by at about the 1 minus 0.9810, that is 0.10. So this is the condition we are taking here. Beta probability x does not belongs to C, H naught is false. Probability x greater than T, then lambda is equal to summation of x is equal to 0, 3 e power minus 2, 2 power x by x factorial. So 1 plus 2 plus 2 plus 2, the power of the test 1 minus b is equal to the simplification we are writing here 0.1429. Example 4.2. So one example we have seen here. In a bag, there are 10 balls. Most important, 10 balls M, which of the more are white, which are white, the remaining 10 minus M are blue. So T, to test the hypothesis H naught, M1 is equal to 5 against M1 is equal to 6, sample size 3 balls is selected without replacement we are taking here. The null hypothesis will be rejected. The sample contains 2 or more white balls. Find the size of the test and its power. So in case of the probability of mass function, if x greater than m, mcx 10 minus 5c 3 minus x, that is 10c by 3. ఎందుకంటే ఇక్కడ చూడండి m 5 ఇచ్చినాడు కాబట్టి 10c 5, 3 balls ఇచ్చినాడు కాబట్టి 3 minus x is equal to 0, 1, 2, 3, 10c 3, m is equal to 5 is the best test against m1 is equal to 6 we are taking here. So c is equal to x is equal to 2 or 3 వాడు ఇచ్చినాడు అక్కడ. So therefore size of the test alpha is equal to probability of x belongs to C, that is this is h naught. This is h naught. So summation of x is equal to, we are simplifying here, 5cx and 5c3 minus x 10c3. We are simplifying 5cx and in place of x is equal to 2 and 3. So we are writing here that simplification of 0.4167 and 0.883 is equal to 0.005. So therefore, power of the test 1 minus beta, probability of x belongs to ch by 1. 6cx minus 4c minus x, that is also 0.367 is the simplification of this value. Another problem we are taking here, x follows an exponential distribution with mean theta. To test h naught is equal to 0 is equal to 1 against h1 theta is equal to 2, a sample size of 1 is taken, then null hypothesis rejects x greater than 1. So find the probabilities of type 1 and type 2 errors. So for type 1, type 2 errors, find out the amount and the power of test also here. So therefore, okay. F of x comma theta 1 by theta e power of x minus theta, the probability of function x. So e power of minus x by theta, theta is x greater than 0. So 0 is equal to, otherwise the condition we are taking here. So therefore, list h naught is equal to theta is equal to 1 against theta is equal to c x greater than 1 x belongs to c h naught x greater than 1 or theta is equal to 1. Integration of 1 to infinity e power minus x dx is equal to integration that 1 e power minus 1. So b probability x belongs to c by h1, probability of x less than or equal to 1, theta is equal to integration of 0 1 1 by 2 e power minus x by 2 dx, that is 1 minus e power minus 1. The power of the test 1 minus beta is equal to e power minus 1, we have to write here. Then another example we have taken here, a single observation is selected from a normal distribution with mean theta and variance alpha square is equal to, the null hypothesis h naught is equal to 50 is not rejected, x less than or equal to 75, otherwise h1 is equal to theta is equal to 60 considered to be true. Find the probabilities of type 1 and type 2 errors also we have to find out here. So here the probability of density function of x is f of x comma t 1 by root 2 n 1 by 5 e power minus 1 by 2 x minus theta by 5 by whole square minus infinity to less than x less than infinity minus infinity to theta to less than infinity. So h naught theta is equal to 50 against h1 is equal to theta is equal to 60. So therefore x1 greater than 75 we are taking here. So alpha is equal to probability of x belongs to h naught, probability of x greater than 75 theta is equal to 0. So probability x minus 50 by 5 greater than or equal to 5. So probability that condition z greater than or equal to 5 we are right here. So the condition of integration of 5 to infinity we are taking z greater than 5. We are writing here integration of 5 to infinity 1 by root pi e power of 1 by 2 z square dz we are writing here. So b probability x does not belongs to h1. So probability of x less than or equal to 75 theta is equal to 60. The probability that is 60 we are taking here x minus 60 by 5 less than or equal to 3. The less than or equal to 3, the probability of z less than or equal to 3 we are taking here. And the 60 low less than or equal to 3 when we got infinity. Integration of minus infinity to 3. 1 by 2 root pi e power 1 by 2 7, that is a simplification of this one. So what is statistical hypothesis? When will you use statistical hypothesis? Simple hypothesis. Gamma p type 1 type 2 error we are summary. So listen here one summary point, so you can learn here. Summary: an assertion or statement about the parameters involved in the probability mass or density function of random variable is called as a statistical hypothesis. A hypothesis that specifies a unique probability distribution is called a simple hypothesis. If that it is not case, then it is a composite hypothesis. And to specify a unique probability component as a simple hypothesis, if not that case is called as composite hypothesis. We are telling here. And a hypothesis of no change or no difference is called null hypothesis, and it is denoted by HO. Any hypothesis which is rival to the null hypothesis called as alternative hypothesis and is denoted by H1. A test of statistical hypothesis is decision rule procedure which helps to take a decision whether to reject the null hypothesis or not based on the information contained in a sample taken from the population. In testing of statistical hypothesis, when we reject a null hypothesis when it is actually correct, that is called type 1 error. The type 1 error is denoted alpha and is called as level of significance or size of the test. On the other hand, we do not reject the null hypothesis that it is a false the error that is a major called type 2 error. Already I told the probability type 2 error denoted by beta. 1 minus beta, the probability of the rejecting HO when it is false is called as the power of the test. So critical region also the region that space generated by sample points, whether the null hypothesis rejected sample belongs to the space. A test of a statistical hypothesis specifies a critical region. Alternatively, the choice of a critical region defines it. So therefore 0, 1 such that so therefore, x belongs to C, where if x does not belongs to C, that is called as non-randomized function is a critical region, is the main important functions in this one. Tomorrow, problem based on Neyman-Pearson lemma, problems on near Neyman-Pearson lemma, and unbiased critical region, randomized test function. Tomorrow we will learn in the class. Thank you, one and all.